Here's another example. We want to sketch the region R and evaluate the double integral of f over R. And since y is my first variable of integration, the function is, of course, sine of x squared times cosine of y squared, or we'd call that sine squared of x times cosine squared of y. And I have limits of integration 0 to pi over 2, but I don't know for sure what the variable of integration is. But now I can say, well, since y is first, then this is y equals 0 to y equals pi over 2. And the x limits are x equals 0 to x equals pi. And what that's describing is this rectangular region. X is going from 0 to pi, and y is going from 0 to pi over 2. So that's the region, and this is the function that's over that region. So we're going to sketch that region and evaluate that double integral. And here's a picture of, this is the function, by the way, I defined it, sine of x squared times cosine of y squared, where as we call it, sine squared of x cosine squared of y. And here that function is, remember I'm in permanent radian mode with my software, so what we're finding is what's the volume under this surface over this. I don't know if you can see that this is pi over 2, about 1.57 this way, and 0 to pi this way. Granted, this is a square. I can't make my software show that really any differently. I don't want to run this out to 3. I guess I could do that, but if I did that, then it would look like I was finding more volume than I am. So I could do that if you'd like to see what it would look like. And that way the scales, there, equal scales. There, I did it. I didn't know I could do that easily. That's what I'm really finding. I'm finding, see the region R, let me turn this around so it looks like the picture above it. There's the region R, kind of like the one above it, only a little bit bigger. And this is the region R, and this is the volume of that piece that's over it. Okay, I didn't realize I had that choice that I could make equal scales. So that's what we're finding. And so our first task, since we're integrating with respect to y first, is replacing cosine squared with 1 plus cosine 2y over 2. And then integrating that. So integral, by the way, factor out the 1/2, this 2 here, just factor it out to the front. And then sine squared x is constant, so we're integrating 1, which would give us y, and then integrating cosine of 2y, which would give us positive sine of 2y over 2. And so then we put in numbers between, well, our limits of integration are 0 to pi over 2, so we first put in pi over 2, we'd have pi over 2 here, and then sine of 2 times pi over 2, which is sine of pi, so this part goes to 0. And when you put in 0, this goes to 0 again, and so does this. So this whole thing is just pi over 2. So that means we'd have a constant pi over 4 in front of the whole thing, because this pi over 2 times this 1/2 is pi over 4, and then integrating sine squared x from 0 to pi. But how do you integrate sine squared? Well, you make it 1/2, and I factored out the 2, and now that's a pi over 8, times 1 minus cosine of 2x, that's actually from the double angle formula for cosine. But so then integrating 1, we get x. Integrating cosine, negative cosine of 2x, we get negative sine of 2x, and that's evaluated between 0 and pi. When I put in pi, that's sine of 2 pi, which is 0. This is just pi. And so when I put in 0, this is 0, and so is this. So this is just pi over 8 times pi. So pi squared over 8. So does that seem reasonable? Pi squared is a little bit bigger than 9. Does it seem like the area, or sorry, the volume under that surface over this rectangle could be approximately a little bit bigger than 1? And I think, yeah, that seems very reasonable. See, look at the peak here is about 0.8 when x is pi over 2 and y is 0. That should be going all the way up to 1. Maybe that does go up to 1. I'm just not looking at it properly from the side, but it goes up to 1. But it seems like a reasonable answer to be just a little bit more than 1.